Dear friends, today I am going to deal stereoselectivity. It is part of asymmetric synthesis. Okay, it is very important concept in asymmetric synthesis as well as in organic synthesis. Stereoselectivity. You know about selectivity. What is selectivity? Selectivity means if you have some options in front of you, you can choose one of them particularly, and that can be uh, selectivity if you simplify like that. Okay, so what is the selectivity in terms of chemical reactions that you need to understand? Okay, in chemical reactions there are many factors which can influence the chemical reactions yield and the type of products formation. Based on their factors, they can selective reactions some selective reactions predominantly or exclusively go through one kind of pathway of that reaction and yields one product majorly or predominantly or exclusively over the other possible products. So that is selectivity in chemical reactions, right? In a chemical reaction that yields predominantly or exclusively one product over the other possible products by reacting at different uh, functional groups or at different um, what do you say, planes or reaction mechanisms or on different positions. Okay, is known as uh, selectivity in chemical reactions, right? So selectivity can be classified into three types in chemistry, in chemical reactions. One is one is chemoselectivity. Chemoselectivity. The other one is regioselectivity. Regioselectivity. The third one is stereoselectivity. Stereoselectivity. So these are the three kinds of selective reactions exist in chemical reactions: chemoselectivity, regioselectivity, and stereoselectivity. Okay, so I'm going to explain. I'm going to explain individually with good examples, right? So first, let us see chemoselectivity. What is chemoselectivity? You already know about chemoselectivity. Okay, it is also a chemical reaction. It is also a chemical reaction that yields predominantly or majorly one product over the other possible products by reacting at one functional group over the other functional group is known as chemoselectivity. Is known as chemoselectivity. Chemoselectivity is a chemical reaction that yields predominantly or exclusively one product over the other possible products by competitive attack on a functional group over the other functional group is known as chemoselectivity. So I'll give you an example on that. So this is the starting material. If you react this with sodium borohydride, you will get this product predominantly. you will get this product. Okay, so here in chemoselectivity, here there are two possibilities. This is keto functional group, and this part is ester functional group. Okay, ester functional group. So there are two possibilities are there to takes place reaction. One is ester, another one is keto functional group. Among these two options, this reagent, sodium borohydride, predominantly, preferably reacts with this keto functional group instead of this ester functional group, so that you will get this keto group converted to alcohol functional group. Okay, so this ester functional group does not disturbed by this reagent. That means this reagent predominantly, exclusively, right, preferably attack this keto functional group over the ester functional group. This is considered as chemoselectivity. Okay, so this is chemoselective. This is a chemical reaction. In a chemical reaction that produces predominantly, preferably one product over the other possible products by attacking one functional group over the other possible functional groups is known as chemoselectivity. Okay, so this is chemoselectivity, and I'll give you one more example on that. Suppose if you have amine alcohol, aniline amine alcohol, if you react with acetic anhydride, if you react acetic anhydride and in acidic conditions, you will get the product. So this is the product. Okay, so here two possibilities are there to react to take the reaction. Okay, aniline group and hydroxyl group. Among these two functional group, this acetic anhydride reagent preferably reacts with amine functional group or amine group and gives the corresponding product. This, okay, corresponding product. Okay, so in this reaction comes under chemoselective reaction. Chemoselectivity means the functional groups. Okay, so different functional groups. So whichever the more reactive functional group, that reagent first reacts with that one, preferably reacts with that one. So that is about chemoselectivity. That is about chemoselectivity. So here amine and hydroxyl functional groups are there, but this reaction takes place at amine group only. It does not disturb this hydroxyl group, so that preferably, predominantly formed this corresponding product over the other possible corresponding product. This is known as chemoselectivity. Okay, this is known as chemoselectivity. So another example, if I give, so if you react first with catalytic hydrogenation, okay, catalytic hydrogenation, what happens? This product will be formed. Okay, that product will be formed. If you react with lithium aluminum hydride at minus 70 degrees, at minus 70 degrees, you will get that product predominantly. Okay, so this compound starting material has this olefinic functional group and this keto functional group. Okay, so if you react with catalytic hydrogenation reaction, so this exclusively or predominantly this olefinic functional group reacts and gives the corresponding product. In the case of lithium aluminum hydride, about minus 70 degrees, the reaction condition, so preferably reacts with this keto functional group without disturbing, without reacting with this olefinic functional group. So this is also one of the best example for chemoselectivity. Okay, I hope you understand about chemoselectivity. What is chemoselectivity? A reaction that yields predominantly or preferably one product over the other possible products by reacting with uh, a functional group over the other possible functional groups is known as chemoselectivity. Okay, so that is about chemoselectivity. So let us look another category of selectivity reactions, regioselectivity. Okay, regioselectivity, regioselectivity. So chemoselectivity means different functional groups. Regioselectivity means different positions or places, regions. Okay, the reactions takes place. So whatever options or positions, places are available to reaction to takes place, so that reaction takes place preferably at one place or one position, at one region over the other possible regions. That is known as regioselectivity. It is also a chemical reaction. Okay, a chemical reaction that produces preferably or predominantly one product over the other possible products by reacting at one position, by reacting at one position over the preferably reacts with one position over the other possible positions is known as regioselectivity. That reaction is called regioselective reaction. Okay, so I'll give you some examples for that. Suppose this is the toluene, the compounds, the starting material. If you react this toluene with concentrated sulfuric acid, concentrated sulfuric acid, you will get three products, CH3 plus CH3, another product plus CH3. So orthohydroxy, parahydroxy, metahydroxy, toluenes, right? Different groups. So, but in this para position compound forms predominantly or preferably over the ortho. This is about 30%, and this is about 66%. This is 32 and this is 62, and another one is 6%. Okay, so here this place and this place or position or region and this, there are three regions available to reaction takes place, this or this or this. Okay, among those three positions the reactions takes place preferably at para position, at para position. Okay, over the ortho and meta positions. Okay, this para compound forms predominantly or preferably over the other possible isomers or other possible resiomers. So this is known as regioselectivity. Regioselectivity means these are the three regions or three places or three positions available to reaction takes place. But this reaction takes place predominantly, preferably at para position because of some factors. Okay, so here this is about regioselectivity. Regioselectivity. So this is another example I want to give you. If you react with H2SO4 dehydrating agent, in this case you will get two isomers. One is this one, other one this one. This is major, this is minor. Okay, major and minor. Okay, so that means regioselectivity means, so there are first of all so this position is available and this position available for dehydration reaction. Okay, and two compounds are formed in this reaction products, but among them this trans compound is more in percentage. Okay, this trans compound preferably formed majorly or predominantly over the other possible isomer. This is known as regioselectivity. This is known as regioselectivity. Okay, so in the first case it is chemoselectivity. In chemoselectivity, so there is a competitive competition uh, reaction to takes place on different functional group. In the case of regioselectivity, the places or positions or regions. Okay, so the preferable region or place or position will get the predominant product by attacking on those positions, right? So one more example, suppose this is pH. So if you react with trifluoroacetic acid, there are two possibilities are there: CH3, C double bond O, pH. This is major. Another one is CH3, O, C double bond O, pH. This is minor. So that means with this reagent, this product preferably predominantly forms over the other possible product. So because here the reagent chooses or preferably reacts at this position rather than this side position or this side region. Okay, so this is also the best example for regioselectivity reactions. Okay, so these are about regioselective reactions. You don't need more explanation on this in this unit. Okay, the next one is stereoselective reactions. So this is important: stereoselectivity. So what is stereoselectivity? Chemoselectivity means functional groups preference. Regioselectivity means positions or regions computation and preferences. But what about stereoselectivity? Stereoselectivity reactions, uh, the computation between different planes or three-dimensional structure. Okay, the pathway, the mechanism of the reaction, So if it is comes from front side, you will get one stereoisomer. If the reagent comes from back side, you will get the different product or stereoisomer. Okay, so stereo selectivity means different spaces. Okay, if it is come from front side or other back side. Okay, different uh, spaces, three-dimensional structure. So that you need to understand about stereo selectivity for that. Okay, stereo selectivity, the definition for stereo selectivity, uh, a stereo selective reaction, a chemical reaction that produces one stereoisomer predominantly over the other possible set of stereoisomers by reacting in different spaces. By reacting in different spaces, what are the space is different. Okay, is known as stereoselectivity. Is known as stereoselectivity. Okay, stereoselectivity further can be classified into different classes. Stereoselectivity can be classified into substrate stereoselectivity, substrate stereoselectivity, product stereoselectivity, product stereoselectivity. Again, substrate stereoselectivity can be classified into two types: substrate enantioselectivity, substrate enantioselectivity, enantioselectivity, and substrate diastereoselectivity, diastereoselectivity. Similarly, product stereoselectivity can be further classified into product diastereoselectivity, enantioselectivity, product enantioselectivity, and product diastereoselectivity, product diastereoselectivity. Okay, so these are the types of classification of stereoselectivity. Stereoselectivity can be classified into substrate stereoselectivity, product stereoselectivity. Further, substrate stereoselectivity can be classified into substrate enantioselectivity, substrate diastereoselectivity. Similarly, product stereoselectivity can be classified into product enantioselectivity and product diastereoselectivity. So these are the types in this stereoselectivity. Let us try to learn one by one in this class. So let us learn about one by one in this substrate enantioselectivity. First, let us see substrate enantioselectivity. So by name, you can guess what is substrate enantioselectivity. What is enantio substrate enantioselectivity? It is also a chemical reaction. It is also a chemical reaction reagent in which reagent is majorly or exclusively preferred to react with one enantiomer over the other enantiomer is known as substrate stereoselectivity. Okay, it is also a stereoselective reaction in which reagent is majorly or exclusively preferred to react with one enantiomer over the other possible enantiomer is known as substrate enantioselectivity. So I'll give you example: plus or minus ammonium tartarate, ammonium ammonium tartarate. So in the presence of penicillin penicillium glycol, only minus tartarate, minus ammonium tartarate, ammonium tartarate will be separated, will be separated. Okay, so this is the mixture of plus or minus two enantiomers ammonium tartarate exist in this starting material. Okay, and when you react that with penicillium glycol, penicillium glycol, it preferably reacts with plus ammonium tartarate only, so that will form the corresponding complex, and minus ammonium tartarate will be separated from that. Minus ammonium tartarate enantiomer can be separated because the penicillium glycol reacts with plus ammonium tartarate and gives the corresponding complex product. So minus ammonium tartarate will be free. That's how you can isolate plus ammonium tartarate from its mixture plus or minus ammonium tartarate. So this is one of the example substrate enantioselectivity. In this substrate there is a mixture plus and minus ammonium tartarate. Okay, so we are using penicillium glycol reagent. This react exclusively, preferably with plus ammonium tartarate isomer or enantiomer, and gives corresponding product, so that minus ammonium tartarate compound or isomer enantiomer separated from this mixture. So this is stereoselectivity, substrate enantioselective reaction. Okay, so because in this substrate, this is substrate, in this substrate there are two enantiomers plus and minus. So this reagent exclusively or preferably reacts with plus ammonium tartarate enantiomer. Okay, it does not react with minus ammonium tartarate, so that you can easily separate two isomers into individual isomers. So this is one of the example about substrate enantioselectivity. The next one, DL glucose. DL glucose. So DL glucose, if you react that with baker's yeast, okay, if you react with baker's yeast, you will get only D glucose. You will get only L glucose. So that means this yeast preferably predominantly reacts with D glucose and gives corresponding product, and it does not react with L glucose, so that after the reaction you can be able to isolate both the isomers or both the stereoisomers individually with this reaction. So this is called substrate enantioselective reaction. This is called substrate enantioselective reaction. So another Another example I want to give you, pH. So this is the starting material. So the reagent is for this DET and isopropyl TBHP, and next one is titanium isopropyl oxide, and DCM as solvent. You will get pH, and these are the two isomers possible in that reaction. Okay, and this is major and this is minor. So what are the configurations? Sorry, this is major and this is minor. This is 45% and this is 55%. So this is R configuration and this is S configuration. 1, 2 and 3. Clockwise rotation, therefore R configuration. Here 1, 2 and 3. This is clockwise rotation, but the least priority group is towards the viewer, therefore the configuration reverse, it is S. Okay, or S configuration. So in this reaction, substrate stereoselective reaction, so this forms predominantly or exclusively or more majorly. So this is called substrate stereoselective enantioselective reactions. Substrate enantioselective reactions. Substrate enantioselective reactions. Okay. In substrate enantioselective reactions, resulting product may be optically active or not, or gain optical activity or lose the optical activity. That's what happened in okay. So why these substrate stereo enantioselective reactions? Wow, what is the reason to takes place like that? Okay, so how we can explain for that preferences or selectivity in substrate stereo selectivity? So for that you need to understand about transition state energies. Okay, transition state energies. Suppose in substrate you have two enantiomers. Okay, E1 plus E2 mixture, and if you react with some reagent, okay, like A star, and in the next step you will get uh, E1 and A star. This is the transition state. Okay, next E2 and A star. This is also another transition state. After that uh, P1 product and P2 products will be formed. Okay, P1 and P2. One will be major, another one will be minor. Suppose I can say this is major and this would be minor. So I am explaining why substrate enantioselectivity takes place, how we can explain or give reasons for that. Okay, so based on the transition state energy levels. Okay, first, this mixture of enantiomers reacts with this reagent and forms transition states. Okay, and these transition states um, gives the corresponding product. Okay, product 1 and product 2. Suppose I say product 1 major and product 2 minor, how we can justify? Okay, I'll show you the energy diagram for that. So this is delta G, energy levels, and this is the reaction pathway. Suppose, and this is the E1 plus E2 energy. Okay, so E1, this is the P1 product, and this is the P2 product energy level. So the difference between these, this is the transition state energy level. Okay, energy level, and this is about transition state P1 level, transition state energy level. Okay, so in this diagram, in this transition state, these have lower activation energy. Okay, lower activation energy, lower activation or transition energy. Therefore, because of this lower transition or activation energy, this produces P1 very fastly. Therefore, P1 product would be major, P2 product would be uh, uh, lower. Okay, based on these energy levels or transition state or activation energy levels. So if P2 would be formed, it requires more energy. Okay, but P1, it requires only less energy to reach the transition state. So because of that reason, okay, P1 forms more than the P2. Okay, because of this transition state energy levels. Okay, activation energy levels. Okay, so this we can explain why one enantiomer forms predominantly over the other, like that. You can change that. You can based on that based on the transition state energy levels. You can explain for that. Okay, the next one is substrate diastereoselectivity. Substrate diastereoselectivity. Substrate diastereoselectivity. Substrate diastereoselectivity. So that means you have two diastereomers in a substrate. This is the example. This axial at position axial. This is equatorial. Okay. So these are the two diastereomers. If you react them with oxalic acid, okay, and so this would be the product forms, but this product forms from this one only. predominantly. This is fast, this is slow reaction, rate of the reaction. Okay, this is fast rate of the reaction, this is slow. That means this would become this product uh, fastly. Okay, this is slow. That means this converts into the product very slow. Okay, this is about substrate diastereo selective reaction. This is about substrate diastereo selective. So that means in these two substrate mixture, okay, so if you react with this one, so this diastereomer reacts fastly and product forms this product compared to this one. That's how you can separate this isomer from this. Okay, so this is one of the example to substrate diastereo selectivity. Substrate enantiomer selectivity and diastereo substrate diastereo selectivity. Those two you have learned. Okay, substrate enantiomer selectivity means in the substrate there are mixture of isomers. Okay, among them the reagent which we used preferably or predominantly or exclusively reacts with one enantiomer over the other enantiomer. That's how you can separate the enantiomers. That is about substrate enantiomer selectivity. So what about diastereo? Substrate diastereo selectivity means among the two diastereomers, okay, or mixture of diastereomers, one diastereomer reacts preferably and forms the product, corresponding product over the other possible diastereomer, which is slow in reaction. That's how you can separate and you can selectively react the diastereomer which you want to have the product. Okay, next we'll see product stereo selectivity. Product stereo selectivity. In product stereo selectivity you have product enantiomer selectivity. Okay, product enantiomer selectivity. Enantiomer selectivity. Product enantiomer selectivity means it is also a chemical reaction. In this chemical reaction which yields predominantly or exclusively one stereoisomer or enantiomer over the other possible enantiomers by reacting at specific uh, three-dimensional space is known as product enantiomer selectivity. Okay, product enantiomer selectivity. So in this product enantiomer selectivity, substrate requires chiral reagent. Substrate requires chiral reagent. Chiral reagent. Okay, and also substrate requires enantiotopic phases or ligands. So if you want to have product enantiomer selective reaction in substrate, there must be enantiotopic phases or ligands. You know about enantiotopic ligands or phases. Okay, in my previous classes I have already explained about that. And also substrate requires chiral reagent. Okay, chiral reagents. Without chiral reagent Without chiral environment, you cannot synthesize enantiomers or product enantioselective reactions. Okay, so these are the conditions, requirements for the product enantioselectivity. Product enantioselectivity, especially product enantioselectivity. Product enantioselectivity. Product enantioselectivity. So I'll give you examples. So this is the best example, CH3. Okay, if you react with some Z reagent, there is a possibility of two. One is front side, another one is back side. So these two are enantiotropic ligands. Okay, these two are two hydrogens, enantiotropic ligands. Okay, this reagent have a possibility to react with this side hydrogen or this side hydrogen, but this reagent preferably reacts with one uh, hydrogen preferably, so that the corresponding product or product enantiomer will be formed more. So in this P1, two enantiomers possible. Suppose P1 is more and this is less, minor, like that. So this is the example for product enantioselectivity. This is the example for enantioselectivity. So as I already give you this example in the last class, in the beginning of my class. So this is the substrate. Okay, in this substrate, so what is the phase here is the first priority, second priority, third priority, right? Clockwise, rephase. Okay, front attack, okay. So Baker's yeast, if you react with Baker's yeast, you will get this product. So this is forms 99% enantiomeric excess. So this is the best example for product enantioselective reaction. So this is the starting material or substrate. In this substrate, this keto functional group and ester functional group. This is the rephase, okay, front attack. So Baker's yeast, if you react this with Baker's yeast, you will get this product predominantly or exclusively 99.9 enantiomeric excess. Okay, so this is product enantioselective reaction. This is product enantioselective reaction. So another example I would like to give you this acid CH3. So what is the phase in this? Suppose this is the first priority, second priority, this is third priority. Anti-clockwise rotation. Therefore, this is psi phase, anti-clockwise. Okay. So that means the incoming reagent attacks from this side. Okay. So what is that? Lactate dehydrogenase. Lactate dehydrogenase. So this is one of the enzyme. Okay, two enantiomers possible. COOH, hydrogen plus COOH. These are the two compounds forms. So among these two, this is major, this is minor. Major and minor. So what is the absolute configuration of this? This is the first priority, second priority, third priority. It's anti-clockwise. Anti-clockwise. So that means R isomer. And what about this? 1, 2, and 3. It's also anti-clockwise, but S isomer. Okay. So one is major, another one is minor formation with this reaction. Okay. So among this, one forms predominantly over the other possible enantiomer, product enantiomer. This is called product enantiomer selectivity, and these reactions are best examples for product enantiomer selective reactions. Okay, product enantiomer selective reactions. Finally, product diastereo selective reactions. Product diastereo selective reactions. Product diastereo selectivity. Product diastereo selectivity. Just now you have seen about product enantiomer selective enantiomer selectivity. In that you have seen that the uh, substrate requires enantiotropic ligands and phases. That is one of the criteria which requires to carry out that reaction. The another one is um, chiral environment is necessary for that. Okay, chiral reagent must be used in that reaction. Both the conditions must be fulfilled in previous reaction so that you will get product enantiomer selectivity and enantiomer selective reactions. So finally I am going to explain you about product diastereo selectivity reactions. Product diastereo selectivity reactions. So if you want to define this one, so it is also a chemical reaction that produces predominantly or exclusively one diastereoisomer over the other possible diastereoisomers reacting by reacting um, specifically one pathway. Okay, by one pathway or one mm, space over the other possible. Okay, so that's about product diastereo selectivity. That is about product diastereo selectivity. So in product diastereo selectivity, reactant or substrate requires diastereotropic ligands and phases. Okay, so if you want to carry out product diastereo selectivity, in substrate there must be diastereotropic ligands and phases in that. Okay, and the other one, the resulted product may be optically active or inactive, so that depends upon the character of the reagent. Okay, so the best example for that, for product stereo diastereo selectivity, and this is the substrate. In this substrate, this is the F1 and this is the F2. That means two phases, diastereotopic phases are there in this compound. Okay, the incoming reagents like sodium borohydride, two diastereomers are formed in this reaction. Okay, this is major and this is minor. That is major and this is minor. Okay, so this is the example for product diastereoselective reaction. This is the substrate in this example has have two phases, F1 and F2, below the plane, above the plane. Okay, so both the sides are there, front side and back side. So the reagent is able to attack that reaction site from back side or front side. Okay, so if it is um, reacts from back side, you will get one diastereomer. If the reaction takes place from front side, the another diastereomer formed. So in this is more stable diastereomer, therefore it forms predominantly in this reaction. Okay, in this reaction it forms predominantly. So this is about product diastereoselectivity, and this reaction is called product diastereoselective reaction. What is the product diastereoselective selectivity? In a chemical reaction that yields predominantly or preferably one diastereoisomer over the other possible diastereoisomer by reacting at preferable space, maybe front side or back side, is known as product diastereoselectivity. Is known as product diastereoselectivity, and this reaction is called product diastereoselective reaction. Okay, so friends, these are the things you need to understand in this class. Okay, so this is about stereoselectivity in chemical reactions, especially in asymmetric synthesis. If you understand all these concepts and types of selectivities and reactions, it is easy for you to um, understand and predict new synthesis schemes also. Okay, so finally I would like to conclude this class with the important points in this class. Okay, so initially you learned about selectivity in chemical reactions. You learned that so there are some kinds of selectivities in reactions, chemical reactions. Three kinds of uh, chemical selective reactions are there. Okay, one is chemoselective reaction. Chemoselective reaction means in that reaction the reagent reacts on one functional group predominantly over the other possible functional group. So that's why that gives the corresponding product or isomer predominantly. So that is about chemoselectivity. It concerns about the functional groups. So the second one is regioselectivity. Regioselectivity means um, the positions, the regions are competitive attacks. Okay, if the reagent attacks preferably one region or one position, so that gives the corresponding product predominantly over the other possible uh, rhizomes. Finally, stereoselective reactions. Okay, stereoselective reactions concern about uh, stereochemistry. That means three-dimensional structure. The incoming reagent, the reactions takes place on different spaces. Okay, it may be from front side, it may be from back side. Okay, on different three-dimensional planes, so that you will get different possible stereoisomers, but among them predominantly one stereoisomer forms more than the other stereoisomers, right? In stereoselectivity, you have different kinds of classification. Okay, substrate stereoselectivity, next product stereoselectivity. In substrate stereoselectivity, you have substrate enantioselectivity and substrate diastereoselectivity. So in um, product stereoselectivity, you have product enantioselectivity and product diastereoselectivity. So I gave the best examples for that, and if you go through my notes and my lecture, I hope you will understand easily about these concepts. Okay, thank you, bye.